Okay, so when I concocted this title, I kind of realized that what makes the world go round, well, what's the world? What I really meant is the Earth. And that's something that we don't often think about, the driving force that makes the Earth rotate. And in fact, all of this came from the book that David mentioned, The Fourth Phase of Water. And most of you, I think some of you have heard the presentations on the fourth phase of water. We all know three phases of water. We know solid, liquid, and vapor. The excuse me, the book presented evidence that there's actually a fourth phase of water, and there are a few properties of that phase that actually gave rise to what I want to talk about today. Let me just begin by mentioning some of those properties. The first one is that when water, and you can see the water, I think there's a, let's see. So this is water that you see here, and next to the water is some kind of hydrophilic surface. And what we found is that when water meets the hydrophilic surface, it builds this huge zone. This is not one or two molecular layers, but up to millions of molecular layers of water that actually changes its properties amazingly. And we call this, because the properties are so different, we call it the fourth phase of water. And one of the features that it has is that it's got negative charge. And the region beyond that has positive charge. We call it the fourth phase, and sometimes we call it the exclusion zone, because we found that this zone excludes practically everything from it, just like ice. It moves out into the region of ordinary bulk water. So because this region is negatively charged and this region is positively charged, you can actually put an electrode in here, an electrode in here, and extract current from it. So that's one of the interesting features of this. Another interesting feature is where the energy comes from to build this zone of water and to separate the charge. It comes from light. This was rather a surprise to us, but we found that if you expose the water to light, what happens is this exclusion zone, EZ, exclusion zone, fourth phase of water builds, and the charges separate. So we found it really interesting that light, that sunlight, for example, is the energy that drives the buildup of this phase of water. Now, when you think about it, this has led to a lot of thinking about the consequences of this. And one of the consequences that I'm going to be talking about is the rotation of the Earth. Now, I know it's impossible to think of any linkage between what I showed you a moment ago and the Earth's rotation, but I bet that a lot of people here don't really think about what makes the Earth turn. Maybe you do, I'm not sure. Most of my colleagues don't think of it. Oh, you know, it just turns, it spins, right? It started spinning from day one and it just keeps spinning. But when you think about it, you know, most things that spin run down. There are energy losses, and it just doesn't keep going forever. And when we think of the Earth, you know, something may have set it spinning 5 billion years ago or something. You can imagine something spinning for maybe a few times or a few years or even a few hundred years, but 1,000 years, 1,000,000 years, 1 billion years, can it really keep going on that initial energy? Is inertia enough to keep it going? So we started thinking about that, or I started thinking about that. And so what I want to get to toward the end of this talk, and I'll give you a punchline, is that I'm going to suggest to you that the wind blowing over the Earth is actually what's responsible, at least hypothetically, a speculation, for keeping the Earth rotating. And then, of course, the question arises, well, okay, so I'm suggesting that the wind is responsible, but what gives rise to the wind? That's another topic that I bet not too many people have thought about. And I'm going to be suggesting to you that the wind actually comes from charge gradients, lateral gradients of charge, particularly positive charge in the atmosphere. So that's where I'm going. And the way I'm going to do it, I'm going to answer a series of questions, and the list is here. First of all, when we think of charges, charges can exert force, repulsions and attractions. And I think most of us, maybe with the exception of the people here in this audience, don't really think of charges as having really powerful forces. We think, we touch something, we get a shock, and okay, but we don't think of really strong forces. So the first question is, well, how strong are charge forces? If you got a plus and a plus near one another, is it weak? Is it strong? Next question. Where on the earth do charges hang out? Okay, and I want to talk about the earth itself and the atmosphere and the charges that we find there. And the next question, which you could have surmised, is, are there really gradients of charge that we can identify? And then can charge gradients really drive the prevailing winds? And if so, can the prevailing winds spin the earth? Okay, so first question, how powerful are charge forces? Well, one of the phenomena that got me started is something shown by our previous speaker, Don Scott, in one of his books, and that is, if you put a proton next to an electron, let's say at a distance d between them, there are actually two forces that you can think of. The first one is the obvious one, which is the attraction, the electrostatic force. But also, since the two have mass, there's a gravitational force. And the question is, okay, which one is stronger and by how much? And I'm sure most of you will of course, guess that the electrostatic force is larger than the gravitational force, but by how much? See, so that's a question. And the answer turns out to be 10 to the 38th. It's not trivial. It's a huge amount. But I think most of us don't really understand what 10 to the 38th really means. We can understand 10 times or 100 times or 1,000,000 times, but 10 to the 38th. 10 to the 38th is something like the schematic shown here. If you take a proton on the upper left and consider the diameter of the proton, okay, and then consider another distance. If you look at next to the last panel there, you see the solar system. And if you take the distance from the sun to the edge of the solar system, take the ratio of that distance to the diameter of a proton, that's only a mere 10 to the 19th. We need 10 to the 38th. So we're talking about the ratio of the size of a proton to the distance between us and some distant galaxy. That's 10 to the 38th. It gives you some idea about how strong the forces are, the electrostatic forces compared to gravitational forces. Okay, here's another example. You take two copper balls sitting on top of one another, and you start removing electrons from each one of them. That, of course, leaves the two copper balls positively charged. And so the question is, well, how many electrons do you need to remove so that the top one levitates? Okay, and I don't know, maybe you know the answer to that. It turns out the answer is 1 in 10 to the 7th. In other words, only 1 in 10 million, approximately, electrons need to be removed so that this ball, because of repulsion, starts levitating, a really small force. Another example, you take a light bulb, take one of the old-fashioned 120-watt light bulbs, and you know the current goes through the filament, right? And if you could, suppose you could capture electrons, and capture, let's say, 1 second's worth of electrons running through that filament. And suppose you could take that and compress it into, just like a sort of a nucleus of positive charges, you compress it into a dot. And you put one of those dots down at the bottom, resting on the ground, and the other one 1 meter higher. And so the question is, in order to prevent the levitation, and to keep it where it is, how much weight would you have to put on that? Anybody want to take a guess? Lots. Okay, thank you. Okay, the answer is 50,000 fully loaded garbage trucks. I would have shown jumbo jets, actually, there are 5,000 fully loaded 747s, but my son, the artist, couldn't draw them. Okay, and here's finally, not to belabor the point, but it's an important point. Consider this. Suppose you're lying down and somebody is lying or suspended, let's say 1 meter above you, okay? And you remove 1% of her, she's got a lot of electrons and protons, you remove 1% of her electrons and 1% of the electrons of the person below. They're 1 meter apart. And of course, both of them become positively charged, so instead of coming together, which they might like, they're actually coming apart. And the same question, how much weight would you need to put on top of the upper person in order to prevent the levitation? I guess? Lots. Okay, how much is lots? Right, the Earth. The weight of the Earth. And this is not my calculation. You'll see it in Feynman's lectures. He calculated it. I guess he knows how to calculate. So in other words, the point of these somewhat repetitious slides is that charge forces can be astonishing. And if we don't take into account the force exerted by those charges, we're missing something, and probably we're missing something really important. Okay, so one question is, well, okay, so charge forces can be astonishing, but to do that, you need to have separated charges. And the question is, can substances really bear net charge? Okay, and the answer I'm going to say is yes, although chemists will generally say that no, they can't bear net charge because everything tends toward neutrality. But here's an experiment from last week. Here's an electrolyzer, and some of you may know this electrolyzer. You know, it produces so-called health-promoting water. If you drink, it separates the water into negatively charged and positively charged. But they don't tell you it's negatively or positively charged. It's high pH or low pH. And if you were to drink the low pH water, you'd spit it out because it's awful, it kills bacteria. But if you drink the high pH water, pH 10.5, 11.5, something like that, it tastes delicious. And there's a lot of evidence that it actually is good for your health. And you'll find in Japan, for example, this kind of water is if you have any kind of gastrointestinal problem, you go into a clinic, and I'm told by my colleague in Japan that the first thing they do is they put you on this alkaline water, and the government pays for it, so it's got something. Anyway, this has nothing to do with the health benefits of this water. But you can take the water, and you can, as you see on the left side, you can fill a couple of beakers with it. And what we did is we took a simple voltmeter, and we put one probe in the high pH and one probe in the low pH, and voila, half a volt between those. And the half a volt is sustained easily for an hour. That's as far as we went. So yes, you can have sustained charge in vessels of something. This is water. Here's another example. This one's kind of cool if you've seen it. This is well, you start with some beaker of water sitting on the top, and let me. So let's see. Yeah, here's the. So you start with the water, and then what happens is that the water divides into two columns, and the water drips into both. It passes through this ring, and it passes through this ring. By the way, this is called the Kelvin water dropper experiment done by Lord Kelvin. Okay, and the drips go through these, and these collect in this container, and these collect in this container. And what happens is that, well, you know, they drop into there, and after a while, the charge seems to build up in some way, and and then you get a zap, you get a discharge between those two electrodes. It's audible, you can see it, it's really astonishing. And if you look, I mean, and even before the zap, if you stop the flow, these two containers will sustain charge. So one's got negative and one's got positive. And these charges can be amazing if you look at the drops falling into the beaker after a lot of water has got not enough to discharge, but quite a bit, and it looks like this. So at the bottom is the cup, and you can see these traces. These traces are actually falling droplets of water. They should fall into the cup, but the cup has so much charge, and the falling droplet is the same charge, that they get repelled. You can see these traces going upward. So it means that the charge forces can easily defy gravity. So we're talking about really strong forces. Now the point is, substances can bear charge, and charge forces can be huge. So I've answered the first question, how powerful are charge forces? And the answer is much more than most of us think, extreme. Next question is, okay, where on the Earth do charges hang out? And it's known, it's well known that there's an electric field. I remember when I was told that there's, I come from a different field. I don't know what most of you people have known since childhood. And a Russian colleague of mine who was working in my laboratory one day just happened to ask me if I knew anything about the Earth's electric field. And I said, what are you talking about? You mean magnetic field? He didn't know electric field. And he said, you don't know about it? And it was kind of amazing. He said he grew up in Russia, of contemporary age, and he said every middle school student knew about the electric field of the Earth and the negative charge on the face of the Earth. And I guess in this country we don't learn that, or at least we didn't learn that. But anyway, it's well known. It's in the textbooks, especially the textbooks from 50 to 100 years ago. The electric field is about 100 volts per meter at the surface of the Earth. And there must be, therefore, some negative charge on the Earth and positive charge somewhere up there. So essentially, the point is that the Earth somehow bears negative charge. And again, back to the health issue, some of you may know that it's now advocated by people in alternative health or any kind of health to just walk barefoot on the beach. If you walk barefoot on the beach, you're basically soaking up the electric charge, negative electric charge from the Earth, and you need that charge. The body needs negative electric charge to thrive. That's a different issue. I don't want to go into it. So it's called earthing or grounding, depending on where you come from. And in Japan and some of the other Asian countries, mud baths are pretty common, and mud baths are said to have healing properties. And I think the reason for this has to do with connecting to the negative Earth. Okay, so question is, now where does this negative charge come from? The standard interpretation, again, if you read Feynman's lectures, volume 2, chapter 9, lightning. This is commonly thought to give rise to the negative charge on the Earth. We don't get that much lightning, at least in Seattle, maybe here in Phoenix, there's more, but around the Earth, there are huge numbers of discharges, and so it's possible that the lightning comes, strikes the Earth, brings negative charge, and the Earth can't rid itself of that negative charge rapidly enough, and therefore it accumulates a net negative charge. Well, that's one idea. Another idea is that it may come from the Earth's water, and this, as you can see, came from the work that we had done to produce the book that I mentioned. See, if you have EZ water down, the Earth is, of course, filled with water, and if much of that is the fourth phase or EZ water, it bears negative charge. See, so that could be another source of this negative charge. And interestingly, the sun builds this EZ and negative charge. So we have some sort of relationship with the sun. Essentially, we have the sun beating on the Earth, and we have negative charge that builds. And if the Earth is highly conductive, as many investigators think, then these charges will go all around and fill the subsurface of the Earth with net negative charge. So, okay, there's the negative charge, and you might say, well, where do the corresponding positive charges lodge? They're initially together with the water, but many of these protons evaporate into the air. So we have the negative and the positive ones, along with negatives, which actually form clouds, the positive ones are rising up into the air. And as they rise up into the air, you have a situation that looks like this. The Earth is negative, and then you have positive charges that begin rising up, as you see here. And close to the Earth, there's a high concentration of positive charges because those charges are attracted to the negativity of the Earth. But as you get higher up, the protons or hydronium ions tend to repel one another, and they rise vertically and begin to spread out. You have positive charges in the atmosphere and negative charges on the Earth. And you think about that, plus and minus, you have a situation like this, and basic electrostatics tells you that the positive charges are clinging to the negative charges, and so the atmosphere clings to the Earth. And the question that arises, well, if the atmosphere clings to the Earth, it exerts pressure on the Earth. Does this explain atmospheric pressure? The prevailing pressure mechanism is fraught with several paradoxes. We think of pressure arising from the weight of the air. So the weight of the air is pressing down on us. And if you're on top of Mount Everest, there's less air and it's pressing less on you. But if you think about that, we have a gas up there, and the question is, well, we define a gas as you have molecules, and they don't stick together. They actually bounce around and hardly interact with one another. And so if they don't interact except very rarely, then can we easily imagine how they press on the Earth? Or why when you're higher up you have less pressure? It's possible, but it kind of, when you think about it, those isolated air molecules not clinging to the Earth the way I suggested to you, but just sort of hanging out there, it leads to the spectacle of, there's a lot of winds up there, and why doesn't the atmosphere just blow away? Don't know if you ever thought about that. Okay, here's another paradox about the atmosphere and the way we think about the atmosphere, and we're ignoring the positive charges that I told you about. Well, the atmosphere is a mixture of gases. It's not just nitrogen and oxygen, a whole bunch of other gases. So among them, argon is about 1%. It's actually quite a lot of argon that we have in the air, and CO2, of course, causing, apparently, maybe, depending on your belief system, a lot of problems. But argon is the densest of all. And so if argon is the densest of all, you think after all these years that you might have a situation like this. If density really matters, we're fraught with a serious problem. Okay, so we got positive charges in the atmosphere and negative charges on the Earth. And so it's possible, I think, that atmospheric pressure may arise from the positive charges attracting to the negative Earth and pressing down. Quite simple. So, okay, where do those charges hang out? In the Earth and in the atmosphere. Next question. Are there substantial charge gradients, differences of charge that we can imagine? And the answer I would suggest to you is yes, there are both vertical gradients and lateral gradients, the lateral ones being the ones I'm going to be focused on in a moment. But the first is, I mentioned to you that the protons diminish with increasing altitude, and that's shown on the two panels there. Now, suppose you put a test charge, the red one, down near the surface of the Earth. There are a lot of positive charges there. And you'll detect a high electric field. And if you put the test charge higher up, there are fewer positive charges there, and the electric field will diminish. So the field strength diminishes with increasing altitude, and that's well known, well reported. This is nothing controversial. The field strength also increases with sunshine, and this is the interesting part that maybe some people are unaware, but there's enough evidence for this. So if the positive charges are caused by evaporation from the Earth's water, then nighttime there's not much evaporation, right? The charges should be fairly low in altitude. And during the daytime, when you have ample sunshine creating evaporation, those positive charges should rise way up, right? So there should be a big difference between daytime and nighttime. And so therefore, the electric field, which depends on all that charge, should vary with the time of day. So if you have, for example, in the middle of the day, you ought to see a lot of electric field when you're measuring up, well up above the Earth. And at nighttime, it wanes, so it waxes and wanes. And the evidence for that is right here. So this is a plot. This is a bit complicated, but on the abscissa, you have time. And if you look right in the middle at 12 o'clock, that's noontime GMT. That would be Greenwich, okay, in England. And the electric field that was measured up in the air. Look at the oscillation. So first look at the middle one, Africa and Europe, and you can see that the peak occurs roughly 2, 3 p.m. around Europe, just when the sun is kind of has been around for a while, high in the sky, maximum evaporation, all those positive charges high. So you can see that the electric field there is very high. Now look to the right, and you can see the U.S. That occurs 6 or so hours later during our afternoon. So you can see that it doesn't matter where you are, during the nighttime, the electric field is low, and during the daytime, it's high. And look at the differences between them. Look at the Americas, the blue one. You can see that during the daytime, the electric field is 10 times higher than it is at night. This is a huge difference that I think many people are unaware of. So there's a great big difference between day and night, and you can see that there's a gradient. When night meets day, there's a gradient, and also on the other side, the upper right of the figure, there's another gradient. There's a morning gradient, and there's an evening gradient. Big, huge lateral gradient of positive charge. So, do substantial charge gradients exist? Both vertically and horizontally. Okay, now, can those charge gradients drive the prevailing wind? So, think about it. Seattle, on the left, we're snoozing and snoring, and we haven't really gotten there yet. And New York is beginning to be bathed in sunshine, and if it's bathed in sunshine, those positive charges are rising up into the atmosphere. But at nighttime, there are very few of those. So there's a lateral gradient. Those charges repel one another. They want to get away from one another. Where do they go? Well, they're going to go to the left in this. And if the charges are moving, the charges are at least dragging the air with them, because these charges are either protons or more likely hydronium ions, and they're either dragging the air or they may be attached to the air, bound, for example, to electronegative oxygens or nitrogens. So the air is going to move also, and if the air moves, basically we have wind. So I believe that charge gradients can create wind, especially the large gradients with powerful forces that we're talking about. So there's a morning boundary and the evening boundary, and I think those give rise to something interesting and characteristic. Here's the morning boundary. Okay, again, New York has received its sunshine, and Seattle with the Space Needle is still dark, and we have this charge gradient. The charges is morning, the charges are beginning to rise up, and there's going to be a wind that goes across that gradient toward Seattle. Okay, now this is also shown on the next slide. Now, sorry, this one's a little complicated too, so let me explain. So this is the surface of the Earth spread out. So we have nighttime in the center, and we have morning on the right side and evening on the left side. Now, start on the right side and morning, and remember that's just what I was talking about. The wind is blowing from the east toward the west, and it's not a strong wind because the charges on the right side are just beginning to rise up. There are not so many. And it causes a wind, you might call it a morning wind, and the wind blows from east to west, and that's known as the trade wind. Trade wind blows gently. It's what got Columbus to the New World. Now look at the other side. This is the left side is the evening. Okay, and by the evening, mid-afternoon, late afternoon, the charges are way up high, and the gradient is in the opposite direction. It blows from the late afternoon toward the evening, so it blows from west to east. And anybody who's flown knows that there's a wind that blows continuously up high. It's called the jet stream that flows from west to east, and it's pretty strong, 100, 200 miles per hour. So if you fly to New York, it's quicker than if you fly from New York to Seattle or Los Angeles. So I think we can understand that this high wind is going to be stronger. This high westerly wind is going to be stronger than the low easterly wind because there are many, many more charges by late afternoon, by mid-afternoon to late afternoon. So I think those two gradients, from the morning gradient and the evening gradient, could perhaps adequately explain why we have trade winds and jet stream. So the question was, can charge gradients drive the prevailing wind? And I've shown you some evidence, suggestions that maybe that could be the case. Okay, now, can the prevailing wind spin the Earth? Well, you don't, if you think about it, you really don't need a whole lot to, you have a wind that's blowing at 100 or 200 miles an hour. Actually, you know, the Earth is spinning itself, right? The Earth is spinning at what is it, roughly, I think, 1,200 miles per hour compared to the reference frame of the cosmos. And the wind is going, the jet stream is going 100 or 200 miles per hour faster. So it's like the jet stream is blowing, and it could be blowing the Earth, and the Earth can't quite keep up. So it's a little bit slower, and that's why we have a jet stream relative to the Earth that's 100 or 200 miles per hour faster. So I think it's possible that we don't need these tall peaks. This is obviously just illustrative, but all you need is a gradients and something rubbing on the Earth, or rubbing on some protrusions. So the advantage of this kind of wind mechanism is that, so the rotation of the Earth now no longer depends on the inertia. As I said, maybe you think differently, but it's difficult for me to imagine that inertia could keep us going for 5 billion years. It's a lot of time. And also, the sun's energy is the ultimate driver, because remember, the sun's energy is what splits the charge in the water, which gives rise to the positive charge. And so it all comes back to the energy from the sun. And so the conclusion from this is that the reason the Earth keeps spinning is it gets energy from the sun to make it spin. It just doesn't do it. It's known that the rotation speed of the Earth is not constant. It fluctuates even by the day. If the Earth turned by inertia, there shouldn't be fluctuations. There are fluctuations, and so this can explain it. So the question is, can the prevailing wind spin the Earth? And I think the answer is possibly. Perhaps that could be. Finally, the last few slides, this is a sort of extra. And so I'm suggesting to you that there's charge flow around the Earth, right? Charge flow, wind. And I want to touch on magnetic fields because charge flow, current, magnetic fields, they're kind of tied together. And with those charges constantly, like jet stream, constantly flowing around the Earth, basically, oops, sorry. Basically, we have a current that's flowing around the Earth. So think of a current now flowing around the Earth from west to east. And think about what we know from basic electrostatics and dynamics. If we have a current flow going this way, we have a magnetic field using the right-hand rule as shown here. Now think about applying this rule to the Earth. So the horizontal arrows, that's the wind, that's the jet stream that blows constantly around the Earth. It's a current. The current is flowing around the Earth. And if you have a current flowing that way, then those thicker lines show the magnetic field. So it's possible that you can actually get magnetic field occurring just from those charge gradients, creating current that flows around the Earth. So it's possible. I mean, we think that the Earth's magnetic field comes somewhere from the core of the Earth, but nobody's ever been there to make that measurement. And it's kind of odd that you got a magnet sitting there, but the angle of the magnet keeps changing, which it does. Sometimes it even flips. That's not so. I mean, we're really not sure that the magnetic field arises from the core of the Earth. And I'm suggesting to you that it's possible that the Earth's magnetic field arises externally and not internally. So I draw some conclusions, and I don't really mean that they're conclusions. I mean they're speculations. I've shown you very little evidence. I've shown you just a few ideas that have stemmed largely from the book that I produced and the ideas that went into it, and a bit of evidence, but mostly just logical sequences. And the first one is not is well known, and we all should know it, that charges can exert enormous forces. Sometimes we attribute phenomena to gravitational forces. For example, the settling in a beaker of water with some particles, we think of gravitation, but that beaker of water contains enormous numbers of charges. The charge forces outweigh the gravitational forces enormously. Remember, 10 to the 38th. The Earth bears negative charge. Again, there's a lot of evidence for that. Evidence starting more than 100 years ago and continuing. It's just that it's not really well known. The atmospheric scientists know that the atmosphere is full of positive charge. Oddly, it doesn't seem to me, I've never seen anybody make the suggestion that plus attracts minus, that atmosphere attracts Earth. It seems almost a no-brainer. One has to calculate how much force, but it seems like a really simple and easy interpretation of atmospheric pressure, that the atmosphere clings to the Earth because plus and minus attract. It's the sun's energy that builds that atmospheric positivity through evaporation. At night, there's not much evaporation, not much atmospheric positivity. And because of the regions between sunshine and darkness, you have lateral charge gradients. And remember how strong the force of those charges it can be. And so that inevitably drives winds, and winds create friction. And the question is whether that friction is sufficient to create the Earth and keep it spinning and giving us day and night. And it's possible that those charges may actually create the Earth's magnetic field. So I guess I would like to conclude with the fact that the universe, or at least the Earth around us, is indeed electric, as I know many of the people here would like to think. And also the point is that, you know, alternative theories can sometimes make sense, and I end with one example of an alternative theory. This is an alternative theory for global warming and the rise of the sea. Suggest an alternative mechanism, and thank you for listening. Thank you. Thank you.